welcome again to my Physics Online video supplement series. In today's video, I want to introduce and talk about the topics of force and motion. This corresponds basically to the fourth chapter from the College Physics OpenStax textbook and similar chapters in other books, and in fact in many of these books it'll take up 2 chapters, but I'm really going to talk more about the basic part of the physics, which is about the first half of OpenStax. So this is going to basically be about Newton's laws and forces and just introducing these concepts. Eventually we will look at what these concepts can be used for, but today's video is just about introducing the concepts themselves. Basically what we have is that we want to look at why is it that things accelerate. We've already looked fairly extensively in kinematics at describing an object's motion. You could call it almost the formal cause or a description of a formal cause of an object's motion. Now we're getting more into the efficient cause of a motion, and the first part of that is discussing the force laws and how forces interact with objects and what that causes to happen. So forces here basically affect acceleration, and these laws that we're going to look at, we're going to look in context of Newton's 3 force laws, and basically here is the general application of those. We want to look at changes in an object's motions, basically acceleration for now. In a future lecture we may look into a more explicit definition in terms of what's called momentum. So the topic of today's lecture is forces, so we should start off by asking, what are forces? And you could think of a force as something which changes an object's motion in some ways. And you can change an object's motion by, for example, causing the object to speed up or slow down or turn around a corner or change directions in general. So forces are the things that cause an object to accelerate and therefore cause a change in the object's motion. So we experience forces in day-to-day life usually as a push or a pull, and what we need them for is to either start moving or stop moving or turn. You don't need a force to keep moving, save that usually you're moving in an area where there is friction, and so you need a second force in order to counterbalance friction or air resistance or so on. It's important to note that forces are vectors. That means that they have magnitude and direction, and so the magnitude of the force tells you the strength of the force. The direction tells you which way the force is acting in, and therefore which way it will tend to make an object accelerate towards. So this, of course, is a polar breakdown of force, or you could even say, you could expand this into 3 dimensions, and the magnitude is still going to be strength, and then direction might be with 2 angular vectors to give the exact direction. And the other thing that we need to know right off the bat about forces is the units involved with force. So in SI, specifically meters and kilograms and seconds units, we use the Newton. So this is named after the guy whose laws we're going to be discussing today. And 1 Newton is equal to a kilogram times a meter per second squared. So we'll look at explicitly at a law in which we look at how force relates to mass and acceleration. So I guess by doing unit analysis, dimensional analysis, we've already got a preview of what one of the laws might look like. Another unit that's in the metric system, although using centimeters and grams instead of meters and kilograms in the base is what's called a dyne, and that's used a lot in surface tension. So a lot of people watching this are some sort of biology or life science major. That's in particular what the general physics class is aimed at. We're not going to do too much with dynes in here, but in biology, for example, you might encounter dynes a lot in talking about surface tension, for example, like a water strider trying to run across the surface of a lake or what have you. And of course, we might as well mention the imperial unit while we're here. And for the imperial unit, we use pounds. So U.S. customary unit of force is 1 pound. So there's maybe two ways of breaking forces up, or two sections that you can break forces up very broadly and generally into. One is field forces, the other is contact forces. So field forces, there's basically 4 fundamental forces in nature. The field forces are the fundamental forces of nature. Those are gravity, the weak nuclear force, the electromagnetic force, and the strong nuclear force. And I've actually listed them in order of relative strength. So gravity is actually the weakest of these. The strong nuclear force is the strongest, although there are additional stipulations that come into play there, such as that we don't normally have ways of canceling gravity, whereas we do have ways of shielding or canceling electromagnetism. Or nuclear forces tend to work over very short distances, whereas gravity and the electromagnetic force tend to have more range to them. The other option, aside from field forces, which are sort of shown down here in the bottom of this diagram, is the contact forces, which are forces in which you have to have physical contact between the thing applying the force and the thing on which the force is being applied. You're actually touching the object that you're applying the force to. So in this case, you're pulling a spring with your hand, you're pulling a wagon with your hand, you're kicking a football with your foot. So this is sort of a non-exhaustive list of possible contact forces. Turns out, by the way, that a number of these contact forces end up tying in one way or another to the normal force. For example, if you pull on an object, it's because there is some normal force between your hand and the object which allows your hand to hold the object. And that in turn often will tie into, for example, the electromagnetic forces. But for a macro scale, we can basically treat these as just being contact forces and forget about the interaction of individual electrons and protons. So let's talk about Newton's laws. The first of Newton's laws was actually formulated in the late Middle Ages. We have records going back to about the 14th century with a natural philosopher named Jean Buridan, who was a professor of natural philosophy, or natural theology, I think is the correct term at the time, at the University of Paris. And despite his various theories and contributions both to physics and to philosophy, one of the things that he's actually remembered for today is the dilemma of Buridan's ass, and this little diagram shows what that dilemma is. It basically could be summarized as if you put a donkey between 2 equal piles of food that are equally far from him, then the donkey can never make up its mind as to which one to go to if all else is equal. That aside, though, the important thing for our class is Newton's first law, and how Buridan came to formulating Newton's first law is he was commenting on one of the very popular works of the day to comment on among scholarly circles, which was the works of Aristotle. Remember that 14th century, this would be, he actually was around the mid to late 1300s. This is only about 100 years removed from possibly the most famous of the medieval philosophers, St. Thomas Aquinas, who in turn was famous for sort of taking Aristotle and baptizing him into the Catholic religion that was supposedly flourishing within Europe at the time. And so Aristotle's works had been recently discovered and translated into languages spoken in Europe and brought to Europe, thanks in part to actually the Crusades, and thanks in part to interaction with the Moors in Spain, Spanish Christendom and Islamic Christendom. So they were a topic that was being discussed, and of course Aristotle was sort of a pre-Christian philosopher, therefore his philosophy tended towards ideas such as that the universe had an infinite age, and he would not have agreed with the biblical account of creation in time. And Buridan himself was a Orthodox Catholic theologian, so he believed in the idea of creation in time and was trying to reconcile creation in time with some of Aristotle's works on astronomy. What he basically said was he was trying to determine how is it that planets can remain in motion around in their orbits. His commentary, though, was specifically about how is it that these planets can stay in orbit without an angelic being sort of moving in through the ether, through the space between stars, and pushing the planets along, which is one of the common theories of the day. Basically, what Buridan ended up saying was that if there exists no net external influences, like a force acting on an object, then the object will retain its initial quantity and direction of motion until such a time as there is a force acting upon it, specifically a net force acting upon it. So this was basically the first formulation of Newton's first law. It was then given some context by Sir Isaac Newton. Sometimes this law is summarized as objects at rest tend to stay at rest, and objects in motion tend to stay in motion. So the correct way of saying it is that if no net force acts upon an object, or if the net force acting upon an object is zero, then the object will not change its motion. In other words, it will have no acceleration to its motion. It will neither speed up nor slow down nor change directions. And it's worth noting here that the net force is the vector sum of all external forces acting upon an object. So if you wanted to determine the net force acting upon an object, you'd need to figure out all the forces which act upon that object, figure out what direction, figure out what magnitude, and then add those forces as vectors. And this property of objects, which makes them tend to retain their original state of motion, is called inertia. That's the tendency of an object to retain its original state of motion so long as no external forces are, well, forcing it to change. So mass is the means that we have of measuring inertia. Mass is how much matter or stuff there is in some object. And the more matter an object contains, the more massive that object is, the more inertia it has, and thus the more resistance it has to changes in its motion. It's worth noting that mass, because it is how much stuff an object has or how much matter an object has, mass is independent of gravity. That means that whether you are in a high gravity field such as Jupiter or even the Sun, or whether you're in a lower gravity fields such as on the Earth, or whether you're even in deep space where gravity is effectively zero, your mass does not change. And the units we use for mass are kilograms for the SI unit, grams if you're using the CGS unit, and in imperial units you use the slug. That's a unit we don't really hear used very much anymore. For some reason we don't talk much about slugs in everyday life in reference to mass. Even here in the States where we're using the imperial system, we usually just talk about the object's weight, or we say something metric and talk about the mass in kilograms. So that's what mass is. On the other hand, there's also weight. And weight is basically the force exerted by gravity on an object. So on the Earth, or near the Earth's surface, the weight is going to be given by the mass of the object times the free fall acceleration, 9.8 meters per second squared. So we often use an Fg for force of gravity, and that's interchangeable with the word weight. So the weight is the mass times the free fall acceleration. If you have a 1.00 kilogram mass and you put this mass somewhere on the surface of the Earth and you try to weigh it, then in the metric system, in the SI MKS system, you should get a weight of 9.80 newtons. And for what it's worth, if you took a 1 slug mass on the Earth, you get a weight of 32.2 pounds on the Earth. For what it's worth, this weight of 9.8 newtons is approximately equivalent to a weight of 2.2 pounds in the U.S. customary or other imperial systems of measurement. So that's the rough conversion rate, and you can try to work out the rates from kilograms to slugs, or from kilograms to weight in pounds, or what have you from that. By the way, if you were to leave from the Earth, then the weight is going to change. So if you were to go from the Earth to, say, the Moon, where gravity is about a sixth as much, then this mass should still remain 1 kilogram, whereas this weight should be 1/6 of 9.8 newtons, which is about 1.63 newtons. The other thing that's worth mentioning in the context of weight is what's called weightlessness, and that's the apparent removal of weight. So you get actual weightlessness if you're in outer space, very far away from any gravitational fields. There's even some small microgravity when you're in space near the Earth or near the Moon or near an asteroid or what have you, but you will feel effectively weightless there. And if you go far enough away from our solar system, maybe from our galaxy, etc., you might reach a region in space where gravity itself goes pretty much to zero, and then you have true weightlessness. On the other hand, you can try to simulate weightlessness by entering into free fall. So for example, that's how they maybe could train astronauts for space flight. You put them in an aircraft, the aircraft flies very high up, and then at some point the aircraft kind of does a dive, and that simulates weightlessness because the airplane could be falling at the same free fall acceleration that you would have inside the plane. Similarly, if you're standing in an elevator car and the elevator car starts accelerating downward, you will start feeling lighter while you're in the elevator car. So if you weigh yourself in the elevator, you'll initially feel heavier, and the scale will say that you weigh more when you first accelerate upward, and then as you come to a stop at the top floor, you'll feel momentarily lighter, and the scale will read momentarily lighter. And similarly, if you accelerate downward from the top floor, initially you'll be light, and then as you come to a stop at the bottom floor, you'll be heavier than normal. If the elevator were, for example, to snap, the little cables holding the elevator were to snap, and you were to plummet with the elevator, you'd feel pretty much weightless for the entire fall down until you hit the ground. Hopefully it's not too much of a fall though. So let's work a few short examples at this point, now that we've talked a bit about weight and mass and force and whatnot. So our first example is, how much does 2 kilograms of silver weigh on the Earth? So to get the weight, we use that the force of gravity on the Earth is the mass times the acceleration due to gravity, or the free fall acceleration. So that should be 2.0 kilograms times 9.80 meters per second squared. So if you plug these guys into your calculator, then what you will get is the following: 2.0 kilograms times 9.80 meters per second squared. So you get 19.6 kilograms, 19.6 newtons. And since we only started with two significant figures here, we should probably round this off to 20 newtons. And so I should add at this time that a short, quick calculation method for estimating the weight of an object on Earth is that every 1 kilogram is approximately 10 newtons, and so every 100 grams is approximately 1 newton worth of weight on the Earth. Okay, next example. How much would this same 2 kilograms of silver weigh if we went to Mars instead of to the Earth? On Mars, the local free fall acceleration is about 3.7 meters per second squared. It's about a third of the value on Earth. Maybe a little off from a third, but 3.7 meters per second squared is the free fall acceleration on the surface of Mars. All right, well, on Mars, we can write that G for Mars is 3.7 meters per second squared. We had a mass of 2.0 kilograms. So the weight of this thing should be the mass times the free fall acceleration. So that's 2.0 kilograms times 3.7 meters per second squared. So let's see what we get for that. 2.0 times 3.7 gives us 7.4. So the weight on Mars of this silver is going to be 7.4 newtons. So you can see here that that's roughly a third of the weight on the Earth. In fact, it's a little more than a third of the weight on the Earth. Third example, shifting gears a little bit. Suppose that you have an object, like a stationary cart for example, and there's no friction, and you have one person applying a force of 150 newtons to the east and the other person applying a force of 250 newtons to the west. So how much force do you need to apply to that object in order to keep it stationary? In other words, in order to keep the object from moving. So the condition that we want is for the acceleration to be zero, and in order to do that we need the sum of forces to be zero. This symbol right here, for those who aren't familiar with this notation, just means sum of forces. So the sum of forces in this case is going to be the force from John plus the force from Paul plus the force from Peter. So we need to see what are those, what forces do we need for this to be in order for the whole thing to be equal to 0. And we notice that the force that John applies is going to be entirely in the east direction. So he's applying 150 newtons east. That means that he is applying in Cartesian coordinates 150 newtons, 0 newtons. And the force that Paul is applying is given in this problem as being entirely to the west. So this was 250 newtons, west. So that is the same as minus 250 newtons, 0 newtons. So the north-south direction doesn't matter. We just need to look at the east-west direction. So we can write this as force of Peter is going to be that plus 150 newtons minus 250 newtons is equal to 0 newtons. So this is how we figure out the force that Peter needs to be applying. So this difference right here, of course, is minus 100 newtons. So the force of Peter minus 100 newtons is 0 newtons. And therefore, we can write that the force that Peter needs to be applying should be plus 100 newtons, which is the same thing as saying, since we've defined the positive direction to be east, Peter should apply a force of 100 newtons, in the eastward direction. So if that happens, then this object should be balanced. And if the object is balanced, then that also means that it will have no acceleration in this case. So to keep the cart stationary, we need 100 newtons to the east from Pete. So I wanted to throw out a few questions that you should be pondering as you've watched this video so far. I'm not going to answer these questions right now today, but they are things that I will discuss for those of you who are watching who are going to be in class on Monday. The questions that I want you to ponder that we'll discuss next time in class are: which would you rather have? A Newton of gold on the moon, a Newton of gold on the earth, or does it matter whether that Newton was weighed on the moon or on the earth? Secondly, does an object which is moving need to be acted upon by an external force? Third, if the object is not accelerating, is it true to say that there are no forces acting upon that object? And fourth, if an object is accelerating, is it true to say that there is at least one external force acting upon the object? Okay, the second thing I wanted to discuss today is Newton's second law. So far we've looked at Newton's first law. Now we need to look at Newton's second law, and as it turns out, Newton didn't formulate his second law either. At least he was not the first one to formulate it. Instead, a man in the previous generation of scientists and philosophers named René Descartes actually formulated it before Newton. Descartes, by the way, was roughly contemporary with maybe about 100 years before Newton's time. So what both of these guys said in their formulation of it is that if you know how much force you're applying to an object, then you can figure out what the acceleration of the object is, provided you know what the object's mass is. So the actual formulation that is commonly used is that the sum of forces external to an object, which are acting upon an object, are sometimes also called the net force acting on the object, is equal to the mass of the object times the acceleration of the object. So the net external force is the same thing as saying the sum of all forces that are external to the object which are acting on the object. Take every force that is outside the object acting upon the object, add them together as vectors, and you have the net force. That net force will have the same magnitude and direction as the mass of the object times the acceleration of the object. So let's go ahead and try another couple examples. So let's go ahead and look at some examples of Newton's second law. So the first example is that you now have just John, and he's applying that same force of 150 newtons, still going eastward, but this time there's no Peter and no Paul, and we're just pulling on some box, and the box is on some surface that is basically frictionless. So in other words, imagine that this is the only force acting on the box, or that this is the net external force acting on the box. Given that this box is a 50 kilogram box, what acceleration do we expect? All right, so we've just been given that the net force is going to be equal to just whatever force that John is pulling with, and that is going to be 150 newtons, comma, east, or 0 degrees. And we've been given that the mass of the box is 50 kilograms. So we want the acceleration. So we can use that F net is equal to the mass times the acceleration by Newton's second law. So Newton's second law says this equation. Therefore, the acceleration can be obtained by taking that net force and dividing by the mass of the box. So that means that we have 150 newtons east, and we have a 50 kilogram box. Recall, of course, that when you're doing a division of a vector by a scalar, that you just divide the magnitude of the vector by that scalar. So 150 divided by 50 should give you 3. So that means that the acceleration should be 3 meters per second squared to the east. So this is the acceleration that that box is going to have so long as John is pulling upon it. Suppose now, instead of having a 150 newton force to the east, we have a force of 300 newtons at 15 degrees. This would be basically equivalent to 75 degrees east of north, if you were going to draw it on a map. And suppose that this box is actually 75 kilograms. So what's the acceleration of this box going to be in this case? Okay, just for fun, let's go ahead and draw sort of an overhead view of what this might look like. So the box is right here, and the force that's acting on the box is being pulled in this 15-degree direction. So here's 15 degrees. This, of course, therefore would be the equivalent of saying north 75 degrees east, or 75 degrees east of north. In any case, we apply Newton's second law again, and what we have to work with here is that the net force is again going to be equal to the force that John is applying to the box. And so that means that, recall from Newton's second law, that the net force is the mass times the acceleration. We're looking for the acceleration. So the acceleration should be the net force, but since that's the force applied by John, it is this force divided by this mass. So again, the force was 300 newtons, 15 degrees. And the mass of the box this time is 75 kilograms. So 3 divided by 75 should give us 4. 300 divided by 75 should give us 4. So our acceleration in this case should be given by 4.0 meters per second squared at 15-degree direction. So 15-degree direction basically means that the box is going to accelerate this way at 4.0 meters per second squared. So far, we've basically dealt only with problems in which there's only one force, or if there's more than one force, they're collinear with each other. In other words, the problems we've been dealing with are effectively one-dimensional problems. However, forces can act in more than one dimension. In fact, since we live in a 3D world, forces can be applied in 3 dimensions. And even in 2 dimensions, forces can be tricky to keep track of unless you have some system for doing that. And one method of keeping track of forces, and really of showing yourself how to set up a problem, is to draw what's called a free body diagram. So oftentimes the free body diagram is something in which there is a single object represented as a point mass, and then any forces which are applied to the object are drawn pulling in different directions upon the object. So what we have here is a free body diagram involving some children who are pushing on a wagon with a kid in the wagon, and there's a number of forces that are labeled here. There's a force that the first child is pushing upon the wagon with. There's a force that the second child is pushing upon the rider of the wagon with. There's friction between the ground and the wagon. The wagon has some weight. The floor is holding the wagon up. That's called the normal force. And so what do you do with all these forces if you're trying to figure out what the acceleration of the wagon is? Well, one way that you can do it is you can draw a diagram like this that labels all of the forces at the point of application. You can also label more of a free body diagram of this style, which shows simply the direction and, if you so desire, relative magnitude of all the forces on the object. So friction is acting to the left. The 2 children are both pushing on this object, and both of those are going to the right. The weight is pulling down, the normal force is pushing up. And if you were to attempt to add all of these, you would look at these arrows to see which direction they're pointing in, and that gives you some general idea of which ones are in the X direction and which ones are in the Y direction. And that works for any number of forces that act on an object. Here's one that's actually a slightly simpler system in which just one person pushes on the rider of the wagon. Here's what that free body diagram might look like. And the most critical thing that you're doing in the free body diagram with these forces is showing the general direction of the force, and then of course labeling each force so that you're sure that you've accounted for everything. It is important to label those forces, by the way. This basically lets you know which force is acting in which direction. And you can try to draw the forces to scale if you're given all the forces. You can even try to draw the exact direction if, for example, you're going to do a geometric addition of vectors. But if you're just trying to add forces together using only a Cartesian or analytic method, then it might make sense to show the general direction in which forces act. And it's also important to attempt to show which forces are acting upon which object. So these are sort of my force diagrams or pseudo free body diagrams for a thing called an Atwood's machine. So an Atwood's machine is something that often gets explored in the lab for the context of Newton's second law. Is basically a low friction pulley with a string run over it and a mass attached to each side of the string. And often what happens is that you put a different mass on one side than on the other, and you try to figure out what the acceleration of the system is going to be. So sometimes, for example, you might start with the two masses being the same, and then you start removing a mass from this one and putting it on this one. Or in this diagram, you'd probably remove a mass from this one and put it on this one, and watch the system accelerate and measure what the acceleration is and test out Newton's laws. So that would work basically by noting that there are several forces at play here. There's the string. A force that's carried by a string is usually called tension. So on mass 1, the string is pulling upward, and it gets an upward arrow, and gravity is pulling downward. On mass 2, the string is still pulling upward, and gravity is still pulling downward. You don't necessarily have to label the net force on the system that you're attempting to draw this free body diagram for. Usually that's one of the things you're trying to find. But if you've labeled everything to scale, then it becomes easier to try and label a rough direction, or in this case, the forces actually are still one-dimensional when you split it up into two objects. So you can label that there's an upward net force on one object and a downward net force on the other object. So once you've figured out what the total force is, you apply Newton's first or second law as appropriate to each object. And before I move off of this diagram, I should add that this is also one of the first examples we've seen in these lectures that shows a somewhat of a complex system in which there's actually two different things. These two different masses are tied together by the string, so they are coupled to each other, which means that whatever this one does, this one has to do the appropriate complementary action. So if this thing starts moving downward, this thing needs to move upward, and vice versa. And so in the case of a problem like this, usually the acceleration is such that whatever acceleration this has, this one has. Whatever velocity has, this one has. Albeit this one is going downward and this one is going upward, or vice versa. Let's go ahead and look at some more examples. This time with actual three-body diagrams and two-dimensional forces. Let's say that we return to our friends John and Paul, and that they now are applying some forces to an object. One of them maybe applies an eastward force, the other one westward. Let's draw the free body diagram for this system. Okay, we were just told that the cart that's being pulled upon, and I'm going to represent that by this little box, has a force from John of 150 newtons in the eastward direction. So this would be force due to John. And in the opposite direction, we have the force that Paul is pulling with, and it was 250 newtons. So here's the force that Paul is putting on to this object. So that's all you do for the free body diagram. Now if the angle is involved, is something other than collinear, perhaps this box is sitting on the ground, for example, then that means that there is some gravitational force that should be included, and there's, if it is again sitting on the ground, there's going to be some normal force which is included. So here is what our free body diagram of this object looks like. Again, it was frictionless, so we don't need to include friction, no need for air resistance, etc. So the second part of this example then is, given this pair of forces, if we know what the mass of the box is, what will the acceleration be? And the assumption here, by the way, is that this tack that it's sitting on has negligible friction. It's basically sitting on the ground. There's no friction for whatever reason. Maybe it's on like a lake of ice. Maybe it's on an air hockey table, whatever. And not only is there negligible friction, there's also enough balance from the ground that it's not sinking into the ground or being lifted off of the ground. So what we want to know is, what's the acceleration going to be in this case? So to do that, we use that the sum of forces is equal to the mass of the cart times the acceleration. And to get this sum of forces, we need to look at our diagram and see what forces are labeled. And we see that there are 4 forces acting upon the object. So the sum of forces must be literally the sum of these forces. It's the force from John plus the force from Paul plus the force of gravity plus the normal force. And again, I just mentioned that the ground is perfectly supporting this object so that it neither rises off nor sinks into the ground. That's another way of saying that the normal force and gravity are equal in magnitude and opposite in direction, so those two cancel. And so we're left with these 2 forces, which were given in the problem. So the sum of forces is going to be equal to whatever was the force from John, which was 150 newtons to the east, plus the force from Paul, which was 250 newtons to the west, as per our diagram above. So that means that this reduces into a 1D problem. So basically we can write that the sum of forces is equal to 150 newtons minus 250 newtons, or in other words, negative 100 newtons. And so that means that the mass times the acceleration is equal to the sum of forces, means that the acceleration should be sum of forces divided by the mass, and that gives us that it is minus 100 newtons divided by 1 kilogram. So this thing is going to be kind of rocketing along with its initial acceleration, because that's an initial acceleration of minus 100 meters per second squared. And minus 100 meters per second squared given that we just defined positive to be east and negative to be west, is the same thing as saying 100 meters per second squared in the westward direction. So that's what the acceleration of this little cart should be, given these two pull strengths from John and from Paul. That brings me to Newton's third law. This one is actually the only of Newton's laws which, as far as I know, was actually formulated by Newton himself. That, by the way, is a fairly common occurrence. You'll find it again in the second semester of physics when we talk about electromagnetism in the context of what's called Maxwell's equations. So Newton only really formulated the third of his laws, but what he did that was so important and why it's his name on these laws and not, say, Descartes or Buridan's, is that he gave context to these other laws with this law. We will discuss the concept of momentum in a future lecture, but once that's introduced and put together with Newton's third law, this basically will tie all of Newton's laws together, and what they tie together with is what's called conservation of linear momentum. So again, we'll discuss that in a future lecture. What Newton's third law actually is the law that some people call the action-reaction law. It basically says that if one object, let's say a ram, decides to exert a force on another object, maybe another ram, then the force that one of the rams is exerting on the other is going to be equal to the other's force exerted back on the first. So these two forces are labeled here to show that they are the same length, so that means the same magnitude, same amount of force, and they are in exactly opposite directions. So in equation form, what that looks like is that F12 is equal to negative F21. And the big implication here is that there are no single isolated forces in nature. Anytime that there is one force, there must be a second force that is in the opposite direction and equal magnitude to that first force. So sometimes we say that every action has an opposite and equal reaction, but it's worth noting, with all that said, that these two forces actually are acting upon separate objects. So this force here and this force here, even though they are in opposite directions and have equal magnitude, they don't necessarily cancel, because this red force is only acting on the ram that's on the right, and this purple force is only acting on the ram that's on the left. One implication of this, and I kind of hinted a little bit at this before when I was talking about Atwood's machine, is that you can make a division of forces between internal forces and external forces. And an internal force is a force that within the context of a system is inside of that system. So an internal force does not affect the system as a whole. For example, if we went back to the Atwood's machine, we would label the whole system as being both of these masses and the string in between them. So this force that's being carried by the string is actually an internal force when looked at as a force within the system. It's a force that's on this string that's inside the system. It pulls on one direction on this mass, the other direction on the other mass. It actually is sort of a Newton's third law pair. Maybe this is an action and this is a reaction, or vice versa. Truth be told, the action is that this string maybe is, this mass is pulling on this string, and so this string must pull back on the mass. And as a result, this string then must pull on this mass, and this mass must pull back on this string. But that tension force becomes an internal force for the system in that we don't necessarily need it in order to solve for the motion of the system as a whole. There are also external forces, such as gravity, which pulls on this mass and which pulls on this mass and is actually outside of the system. We do need to know how much gravity is there and which direction in order to actually solve for the motion of this system. So most forces tend to count as external forces acting on the system. And to make matters a little more complex beyond that, so here, for example, we have a system that it involves a table, the ground, and this computer. So what are the forces involved? Well, there's a gravitational force upon the computer. There's a gravitational force from the computer upon the earth. There is a normal force between the table and the computer. There's a normal force between the computer and the table. So that's your Newton's third law action-reaction pairs in each case. You need to figure out which forces go with which object, and you need to figure out which forces end up being internal and external to the system. For example, if the system includes both the computer and the table together, then this normal force is an internal force. If it includes just the computer monitor, then this normal force is actually an external force acting upon this monitor. And similarly, for the table, this force is an external force acting upon the table. But if it's the table plus the monitor together, these normal forces become an internal force. Similarly, if the system includes the monitor plus the table but not the earth, then gravity is an external force on the monitor-table pair. On the other hand, if our system is going to include both the earth and the monitor, then gravity actually ends up being an internal force. It's sort of what's holding the system together. So that kind of highlights the importance of defining our system of interest. So notice that a force which can be internal to a complex system actually can end up being external to a given object in a simpler component of the system. So case in point, if our whole system is the wall and the diver, then this becomes a sort of internal force. Now, obviously the diver is leaving the wall, so it may not make sense to make that a internal force, but the moment that you define your system of interest to be just the diver, then this force is acting upon the diver, and this force is acting upon the wall, and this is our system of interest. That means that our free body diagram might look something like this. There's weight pulling downward, there's a buoyant force acting upward, and there is the force that this wall is applying to her feet. This force right here, the feet on the wall, is not being applied to this diver, and that's why this force and this force do not cancel out. To return to our Atwood's machine, by the way, you can see how that might break up a little differently depending on how our system is defined. If we want to define our system as being the whole Atwood's machine, then gravity is external force to both masses, but the tension is an internal force. On the other hand, if we're just interested in a single object in the system, single one of these masses, for example, then the tension force becomes an external force, because the tension force actually acts on this mass here upward, and gravity acts downward on the mass. So we need to label that as external forces if we're just considering this mass alone. Or if we're just considering this mass alone, there's a tension force upward, there's a gravitational force downward. If we're considering them together as a system, the tension's in this rope that's inside the system. It's basically being used to hold the system together, but it's not actually acting upon the system as a whole. So I want to go ahead and look at a couple more short examples now. This applies more towards defining our system and looking at Newton's third law and so on. First example, you have an astronaut who's doing a spacewalk. These do happen. Here's a picture of an astronaut actually doing a spacewalk. Ed White II was the first U.S. American astronaut to do a spacewalk. Let's imagine a different astronaut though, and he does a spacewalk, and for some reason his tether snaps, and so all he has left is his tool belt. And he wants to try to apply some force, get some force applied to him to get him to move back towards the space station. And let's say that in throwing the tool belt, he applies 45 newtons to the tool belt. So the question is, what's his acceleration going to be? So what we've been given is the force on the belt, and that was given as 45 newtons. But according to Newton's third law, the force on the astronaut must be equal, but in the opposite direction, to the force on the belt. So that means that the magnitude of the force on the astronaut is also going to be 45 newtons. So the magnitudes are the same, only the direction is opposite. So we're assuming maybe that the astronaut threw this thing away from the station so that it would push back upon him towards the station. Now we need to figure out what his acceleration is. Well, his acceleration in this case is going to be that force that was acting upon him divided by his mass. So we'll call that mass of astronaut. So that's 45 newtons divided by 90 kilograms. That means that he's going to have an acceleration of about half of a meter per second squared. And if we wanted to make it into a vector, it would be half of a meter per second squared toward the station. So wherever the station is, that sort of defines the direction for us. The other part of this example, of course, is what direction should the astronaut throw the tool belt? I kind of answered that question in answering the previous example. He wants to accelerate towards the space station. And in order to do that, he needs to have a force that acts upon him towards the station. And so he needs to apply a force on the tool belt that he's throwing in the direction away from the station, since these two forces have to have opposite directions. So that means that he needs to throw the tool belt in the direction away from the station. Since we've had quite a bit in this lecture, it's worth also restating what Newton's three laws are kind of succinctly. So here, of course, is Sir Isaac Newton himself. Here are his three laws. The first law says that objects at rest tend to stay at rest, and objects in motion tend to stay in motion with a constant velocity unless acted on by an external force. Mathematically, what that looks like is that if you add all the forces together that are acting upon an object that are external to the object and you get zero, then the acceleration of the object should be zero. And if the acceleration of the object is zero, then when you add all the forces together on the object, you should also get zero. The second law, Newton's second law, is the one that's sometimes summarized by saying F equals ma. This basically just means that if you add all of the forces together which act externally to an object, then that net force should be the mass of the object times the object's acceleration. And finally, we have that every force produces a reaction force of equal magnitude in the opposite direction. So for every action or every force that causes an action, there is a second force that is created that causes a reaction of equal magnitude in the opposite direction. That's the F12 equals negative F21. This is a 1-2, not a 12. This is a 2-1, not a 21. that sometimes causes confusion for people. I want to take a moment to give credit where credit's due and sort of show where I got all the various images that I used in these slides. So hopefully as you watch this video and are making notes from it, you're also reading along in your textbook in the chapters on force. So thanks for watching, and farewell for now.